Guarantor assignments. This is the next stage of row. We've cleared out all the reports that we think are now available. We're going to usher in the new reports that have got guarantees behind them. So every block, each core has 3 validators uniquely assigned to guarantee work reports, to get new work in and say, this is valid work. Yeah. With our numbers, V is 1023, VC is 341, multiply 341 by 3, and you end up with your 1023 validators. Yep. That's a pretty simple relationship. Now, it would be a ludicrously bad form to assign validators to the same core all the time. Yeah? Because then they would form cartels. So in order to keep them honest, we keep them rotating around the cores. We actually rotate them quite often. At the beginning of every epoch, we shuffle the validators. So not even the same, they won't even be grouped in the same sets of 3 from the last epoch. Yeah? They'll just be shuffled according to some random function. In addition to that, every 10 blocks in an epoch, we rotate them onto the next core. So if they were in the previous 10 blocks on core 2, they will now, in the following 10 blocks, be on core 3, and in the 10 blocks after that, be on core 4, and in the 10 blocks after that, be on core 5. So at the beginning, for every epoch, we shuffle them, totally random as to what core they're going to be on, and then for every 10 blocks after, we kind of rotate the cores. Yep. All right. Now, we don't store this mapping on chain. We don't need to because it's deterministic. It's deterministic based on the epochal randomness, which we saw in an earlier chapter, earlier section, as eta. And then with this epochal randomness and the epochal phase, we can calculate what any given guarantor or validator, what core index they are guaranteeing. We put this into G. I put it here as GC, but I think, oh no, yeah, okay, okay. I'm still working on this. In fact, this should read, G is in the sequence of NC, NV, and there's another element of this tuple, which is this HK, right? So it's, instead of being a sequence of tuples, it's a tuple of sequences. It's a little bit easier to deal with if it's a tuple of sequences. Good. And this GC is nonsense, it's just G. All right, so let's move on. So we determine the core. We use eta 2 as the epochal entropy. If you remember eta, there are actually 4 items in eta. There's eta 0, which is our current epochal randomness or entropy accumulator. It's where we put in, if you remember, the VRF seal that's in the header. We're feeding this entropy into eta 0 every block. And then at the beginning of an epoch, we take out that eta 0, put it in eta 1. We take eta 1, put it in eta 2, we take eta 2, put it in eta 3. And eta 3 just gets thrown away. So we've got this kind of pipeline of entropy. We don't want to use eta 1. The obvious thing to do is, well, why don't you just keep 3 etas and just use eta 1 instead of eta 2. Problem with eta 1 is it's only just been decided at the beginning of the epoch. And if there's a fork, which there could possibly be, I mean, we can't guarantee against forks until we get to grandpa. And if we're talking about block production, it's possible grandpa hasn't kicked in yet. Which means as we go from one epoch to another epoch, we might see a fork. And if we see a fork, we'll also see a fork in the entropy. Because it will be a different eta 0, because it will have had a different VRF fed into the header. Now, if we use this entropy immediately to determine the what cores have been assigned to what validators, we'll end up with a validator potentially validating on 2 different cores depending on which fork they see. This doubles their workload, which isn't that great. And it also provides potential attack envelopes for someone who's wanting to send something to one validator and that's bad, right? And then just go onto a different fork and say, oh no, actually it was fine because I was actually doing, I was not, that's an invalid work report, invalid guarantee because I'm not even on that core, so you can't even count it. You can't even attribute it to me. So to avoid this possibility, and also to avoid the possibility that further things like SAFROL operation, which selects validators based on this entropy, we avoid using eta1 at all, right? We let entropy just sit there for an epoch and bake and like just stabilize, because it's really unlikely there'll be a fork is going to last a whole hour. Yeah. Almost certainly Grandpa will have tidied anything up within, I don't know, 3, 4, 5 blocks. But even if it's like more than that, it's still very unlikely to be an hour. So yeah, we basically ignore eta1. We always use eta2. Eta3 is there for historical stuff, which we need. It was explained back in the SAFROL section. All right, so we have 2 helper functions here. R, which rotates, and P, which permutes. So we first do the permutation, right? We first do this shuffle based on the epochal randomness, epochal entropy, and then we rotate based on the epochal phase. They look a bit complicated. They're actually pretty simple. So first, the permutation, which is what goes into G. So G is the permute, giving it the some entropy and some time slot. And we also feed in the keys, right? So we're going to ask it to give us the index permutation, not the keys permuted, but permuting the indices, together with the key set. It's very helpful to have it have the key set be separated from the index. You can easily get the permuted keys just by subscripting one with the other. But it's kind of hard to, once you've subscripted it, to sort of get it back out again. So it's kind of, and it turns out it's actually quite useful to have the indices separate in a later stage, as you'll see. So that's why we keep them separate in G. Okay, so we've got the P, which is this permute. Permute relies, in fact, on the rotation. So we're going to, the actual permutation is this shuffle thing in the middle. And then we actually rotate after we've shuffled by T mod E over R. So what's T mod E? Well, E is the epoch length. So T mod E is just the epoch phase. Yeah, going to be somewhere 0 up to 600, not 600, but 599. And then we're going to divide that by R, which is the rotation period, 10, and then take the floor of that. So that's just going to give us how many rotations in we are. So for the first 10 blocks of an epoch, that's going to be 0. For the next 10, it's going to be 1. For the third 10, it's going to be 2, and so on and so on. Yeah, until it gets to 59. And then it'll be the next epoch, and we'll be back at 0. Okay, so that's that. And then if we just quickly go to the definition of R, we're going to take some sequence C and some N, which is the amount that we're going to rotate by. And it's really very obvious, right? We just add N, modulo it by the number of cores, and just make sure we do that transformation in order, and we're done, right? Just moving all the validators through the cores. Good. That leaves us with F, the shuffle function. F is a standard function. I mean, more or less standard. It's on Wikipedia. It's the, I can't actually remember who invented it now, but anyway, it's restated in the appendix, so you can look it up if you need it. What we're doing with the shuffle is we're taking first the entropy, no, we're not taking first, we're taking second the entropy, but anyway. E is the entropy. The shuffle function actually takes entropy as its second argument. As its first argument, it takes the thing that we are shuffling, so this initial sequence, and we construct the initial sequence basically just by saying the first 3 validators get core 0, the next 3 get core 1, the next 3 get core 2, all the way up to core 340, right? So the initial sequence is just the really, really obvious mapping. I guess it's not quite as obvious as maybe just doing a modulo, well, whatever. It's an obvious mapping, and then we shuffle that by this entropy, and we end up with a shuffled mapping, and then we rotate it. Okay? Should be pretty straightforward. Now, G is what the regular mapping is between validators and cores that they should be guaranteeing. It's, as I said, it's eta prime 2, so it's the posterior entropy, second entropy, and it's the posterior time, the new time slot in the header. We also accept work reports signed by guarantors from the previous rotation or the previous shuffle if it's the first rotation of an epoch. Yeah? This is so that, as you might imagine, every 10 blocks we don't have a stall because one guarantor was busy signing, some work reports, guaranteeing some work reports, and then we switched. We did a rotate, we switched to another guarantor, and that guarantor has to start from scratch and pull in work reports and check whether they're okay and sign. This will take a while. It may take a few seconds, and it may be that if that there's just not enough time for them to get this work report before the block is authored. And so we're kind of cool with this. We all right, we'll allow the previous rotation to come in as well. We don't care. Someone's going to get slashed if it's wrong. The worst thing that will happen is one guarantor will end up signing 2 bad work reports in the same block. It's not ideal because they can only get slashed once, even if they do 2 reports. But realistically, slashes will take a little while to kick in anyway, and it might be that they end up getting they put in 2 work report, 3 work reports in contiguous blocks before they get slashed for the first one. So it kind of doesn't really matter. As long as they get slashed at all, the system is secure. All right. So we need to also define a second G star, which is G but the previous rotation. Yep. And so this is a little bit more complicated because the key set is different depending on whether we're at the very beginning of an epoch or we're not. If we're not at the beginning of an epoch, so if we are here, if the subtracting 10 blocks gives us the same epoch number, then it means we should use kappa still, kappa prime, yeah? And we still use the same entropy. But if we're in the first 10 blocks of an epoch, it means that the previous rotation is actually the previous shuffle, yeah? And it is a previous shuffle of a previous validator set. So now we have to use lambda prime, which is the previous validator set, and eta 3, which is the last epoch's eta 2. And that's what we feed in here. And then otherwise, this bit is pretty obvious. It's just tau prime, but minus 10, yeah? Minus r, which, comes in here. All right. Now, G and G star, we're doing well. Now, we know which guarantors, which validators are guaranteeing on which cores, which means all of the hard work really has been done to now be able to recognize what valid guarantee extrinsic looks like. So let's jump into the work report guarantees. So